Okay, so last time we talked about section 4.1. We talked about expectation. We talked about the expectation of a function of a random variable. We talked about we went all the way up to 4.4. Today I'm going to talk about 4.5. Let's get started. Okay, so 4.5 is about something called variance. And what is that? So here's the setup. Suppose you have a random variable on the sample space. And suppose we look at the function g of x raises x to the nth power. That's a function on the real numbers. And I'm assuming n is at least 0. In fact, n is going to be 2 today. So let's set. So now we have g of x is a new random variable. And we give it a name. We denote this by x to the power of n. This is an uppercase x. When we talk about random variables, they're always uppercase letters. Okay, so now this random variable has an expectation. And this is given by, if you remember the formula from last time, we're going to sum up over all x to the n's times p of x. X here is lowercase, and this is the set of, you're summing over all the set of x such that the probability mass function of x is not 0. Because if the probability mass function of x happened to be 0, here x is a point on the real line, p of x would vanish, it doesn't contribute to the sum. This is a name, the expectation of this x to the nth. It's called the nth moment of x. Okay, so for example, if n equals 1, we get the expected value. That's the first moment of x. Okay, so now let's introduce some notation that's used throughout the book. Let's set for today and for every other day now, mu equal to the expected value. Mu is called the mean of the random variable, okay, or the first moment, of course, right? Okay, so then we define the variance as follows. The variance of the random variable x is the expected value of, what do? We take x and subtract the mean off, and that's a new random variable. And then we take the second moment of that. So in other words, we square it and take the expected value. So that's called the variance of x. Okay, so let's derive some properties of the variance. And to do that, I have to clear the screen. Okay, it's very useful to have another formula for the variance. So the formula we gave was the expected value of x minus the mean squared. So what I'm going to do today is give you another formula, so an alternative formula, and it goes like this. The alternative formula is usually easier to compute with. So what you do is you first of all write what this x minus mu squared actually is. It's x squared times 2 times mu times x plus mu squared. Okay, now Actually, I don't want to do it that way. I'm going to do it directly from the definition. That's what I'm going to do. So this is the sum over x, such that p of x is not 0, of little x minus mu squared times p of x. That's the definition of the expectation of a function of a random variable. Now, this sum, inside the parentheses, we can square things. We get x squared minus 2 mu x plus mu squared times p of x. Here, p of x is the PMF, the probability mass function of our random variable. And now this sum breaks up into three sums. The sum over x of x squared p of x minus, I'll bring the 2 mu outside, the sum over x of x p of x plus mu squared times the sum of p of x over x. And the first term is by definition the second moment. The second term, this term here, is the expected value, which is just mu, so it's minus 2 mu squared. And the third term, since the sum of the p of x's over x is equal to 1, it's a PMF, you're going to get mu squared. So this is going to be the same thing as e of x squared minus mu squared, or another way to write it is that it's e of, we square x inside the brackets, and then in the other case we square x, square e of x itself. So this is the formula. So I'm going to put the formula up here and record it. So it's the same thing as e of x, the quantity x squared, minus e of x quantity squared. That's what we've just derived. Okay, so that's the definition of the variance. You can use either formula as the definition because we derived both. We derived it. So what I'd like to do is give some examples. Okay, so here's an example. Let's toss a fair die and let x record the result. In other words, x takes values 1, 2, 3, 4, 5, or 6. So e of x squared, we sort of computed this already. It's the sum over x of x squared. So this is the second moment times the probability of x. And x takes value, remember the sample space here is 1, 2, 3, 4, 5, 6. And the random variable is just going to record the outcome. And p of x is 1/6 in this case, right? So now what are the possible values of x? The possible values of x are 1 through 6. So this becomes 1 plus 2 plus 3 plus, oops, I didn't do that right. That's the expected value of x. I want to do x squared. So it's 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared over 6. And this gives you a 91 over 6 if you do the addition. We also have the expected value of x. We actually computed that for a fair die. It's 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6, which is 7/2. So the variance of x in this case is 91/6 minus the square of 7/2. And if you do the arithmetic, you'll get 35 over 12. By the way, I should say that the variance is a measurement of how far the random variable spreads out from its mean, right? From its mean, from its expected value, how far it is. So in other words, well, let me first save the slide and let me clear the screen. So if the random variable, if you graph it, and it's very spread out like this has a large variance. And if it's very sort of narrowly spread out around the mean, it's considered to be a small variance. This will become clearer later on. Okay, another quantity people talk about is standard deviation of a random variable. So this is the point is that when we form the variance, we're squaring things and we're summing up. So we when we sum up all these squares, we get a number that's we want to renormalize it back. We should take the square root. So the standard deviation does that. So the standard deviation of a random variable x, sometimes it's called sigma, is given by the square root of the variance of x. Okay, so that's the standard deviation. Okay, so I'm going to talk about properties of the variance. These are important properties that can be used. So first of all, if c is a constant, so you can think of that as a random variable from on the sample space, then the variance of c of the constant is equal to 0. And why is that? Because the expected value of the constant is just the constant. That's easy to see. And therefore, if we compute the x in this, well, x is equal to c in this case, so the expected value of x minus c squared in this case is the expected value of 0 squared, and the expected value of 0 is 0. So that's the reason. That's this, and this here is the definition of the variance. Okay, so that's the first fact. Okay, the other fact is called translation in variance. So what is that? So if I take x and add a constant, and then I take the variance, that doesn't change. That the variance does not change. So I'm going to show you why this is true, but I need some more space to do it. Okay, so I'm going to. So we talked about translation invariance. So we have to compute. Let's see why it's true. Okay, so how do we do it? So what we have to do is compute. I'm going to compute moment, the second moment of a translation of a random variable x quantity squared. So what is that? Well, by definition, that's the sum over little x plus c squared times p of x, which is the sum over x squared plus 2cx plus c squared times p of x. And so we're summing over x here. And so we can break it up. So it's a sum over x of x squared p of x plus 2c times the sum over x of x p of x plus c squared, the sum of p of x. We did a calculation like this before, and this is the same as e of x, oops, I should say, this is the sum of the, of the second, this is the second moment plus 2c times the first moment, the expectation, plus c squared times 1. So that's that. Okay, likewise, we know we can compute e of x plus c. That's the sum over x of x plus c times p of x. And that breaks up if you, I'm sorry about that. I had to deal with an emergency. So I'm back. Anyway, I'm in the middle of this calculation, and this breaks up as a sum of the expected value of x plus c. So if we want to calculate the variance of x plus c, we have to subtract what we previously calculated, which is e of x squared plus 2c times e of x plus c squared. We have to subtract off e of x plus c quantity squared. Well, you can check that when you do that, you'll get exactly the variance of x. So that's the translation and variance. Translation and variance proof. This is a proof. Okay. Okay, so we have one other property which is also useful, is that if we take a random variable and we take constants a and b, and we form the expression ax plus b to get a new random variable, we can compute its variance. And let's see what we get. Well, we know we have translation invariance, so the b drops out. That's the variance of a times x. Okay. And oops, I didn't, I actually missed, let me go back to this. There's another property that I want to compute, is that if you take a constant c times x, then the variance has a rescaling property. It's the same as c squared times the variance of x. And this is, I'm not going to do this computation for you, but it's very, very simple. This is a rescaling by c squared on the outside. Okay, so now if you believe this rescaling statement, then this is a squared times the variance of x. So that's another property. So the variance of ax plus b is a squared times the variance of x. And these are the basic properties. And now the rest of my lecture today is going to be just to do some example. Okay, so here's an example. Flip a coin, flip a biased coin with probability of heads is little p, say, and let x be the outcome of a $1 bet on the coin. So if I get heads, I get $1 for my dollar bet. I win $1. And if I get tails, I lose $1. So what's the expected value of x? The expected value of x, well, if I win, I get $1, and then but I win with probability p. And then if I lose $1, I lose $1 with probability 1 minus p. Okay, because I'm betting on heads. Okay. Okay, so what do you get? You're going to get p plus p minus 1, which is 2p minus 1, and this is in dollars. That's the expected value of this. So 2p minus $1, right? You get. So for example, if p is a half, you get 0. But if p is 2/3, if it's 2/3 more likely to land, twice as likely to land on heads as on tails, then you get 4/3 minus 1, which is 1/3. So that's your expected value. Let's calculate the variance of this game. Well, in order to do that, I have to compute, first of all, the second moment. So let's do that. The second moment is if I win $1, I have to, see, the outcomes are 1, and the possible values, p only is non-vanishing on 1 and minus 1. Every other value p vanishes, the probability mass function vanishes on. So in other words, p of x is equal to is equal to P if X equals is equal to 1, because and then if X equals -1, it's 1 minus P. Okay. So the outcome is winning and losing, right? So I win $1, lose $1. Okay, so what do I get? So the second moment is, if I take my 1, I square it and multiply it by P, and then I take my -1 and square it and multiply it by 1 minus P. And if you add these together, you get P plus 1 minus P, which is 1. So that's that. And we know what the mean is, so therefore the variance of X is the expected value of X squared, which is 1, minus 2P minus 1, the expected value of X quantities squared. And you can expand this out, you'll get 1 minus 4P squared plus, I should be minus 4P plus 1, which turns out to be 4 times P times 1 minus P. So that's the variance of this coin flip. Okay, so let's do another exercise related to this one. So here's an example. Let's flip twice and play the same game. So the sample space in this case is heads, 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 tails, tails, heads, tails, tails. These are what I get when I record 2 flips. Okay, so now what do I win? I win, well, if I get heads and then heads, I win $2 in the first case. In the second case, I win, then I lose, so I'm back to 0. Third case, I'm back to 0, and in the last case, I'm back to -2. I lose $2. Okay, so what's the expected value of this game? X is the outcome of my 2 bets. Okay, so I bet on each time I play it, so I play twice. Okay, so what is it? Well, it's going to be $2. I'm not gonna put the dollar sign in. It's 2 times. So what's the probability? So here the probability, I'm going to put it on top, is P squared. Here it's P times 1 minus P. Here it's 1 minus P times P, and here in the last case it's 1 minus P squared. So it's going to be $2 times P squared plus 0 times P times 1 minus P plus 0 times 1 minus P times P, minus 2 times 1 minus P squared. Okay, if you compute what this is, you should get, if I did this correctly, and I think I did, 4P minus 2. I'll spare you the calculation. So it's 4P minus 2. That's the expected value of X. So now let me compute. I want to compute the variance. So let me first compute the second moment. What's the second moment? Well, it's given by squaring this 2 times. Okay, so squaring the 2 times P squared, squaring the 0 times P times 1 minus P plus squaring the 0 times 1 minus P times P, plus squaring the minus 2 times 1 minus P quantity squared. And what does that give us? If you calculate what this is, you'll get it's 4P squared plus 4 times 1 minus 2P plus P squared. And if we expand that out, we'll get 4P squared plus 4 minus 8P plus 4P squared. So this becomes what? What does it become? It becomes 8P squared, 8P squared minus 8P plus 4. Okay, so therefore the variance of x is the second moment. So it's 8p squared minus 8p plus 4 minus what we got for the expected value quantity squared. So 4p minus 2 quantity squared. And I'm going to spare you the calculation in this case. You can do it. It's just you're just going to expand it and let everything cancel. You're going to get 8p times 3 minus p squared. So that's the formula there. So for example, if in the case of a fair coin, if p equals a half, the value of this game should give you 8 times 1/2 times 3 minus a quarter. And what's that? That's 4 times 11 quarters. If I did this right, because it's, what is it? It's 12, it's 11 quarters, which is 11. So that would be the value of the variance in that case. Okay, I think that's enough for this lecture. And I'm sorry about the gap. I had to answer to an emergency in the middle of the video.